well, it's a great pleasure and honor to speak here. So I will speak about some work in progress, meaning that well, something we're trying to do for 4 years. So there is some theorem from 3 years ago, and there are a bunch of things which maybe possibly someone can help me with. So it's about self-avoiding walk. So it's one of those sort of almost integrable models. Oops. Maybe avoiding walk. And again, so we'll deal with the planar case and moreover on hexagonal lattice, and the work which I will speak about is joint work with Hugo Duminil, Copin and Dima Cherkak and Sasha Glasman. So it's one of those very old models. It was proposed in 40s by a well-known chemist Paul Fleury, who was studying behavior of polymers in diluted solution. And his question was that if you have a long polymer chain, how on average will be the position in space and how this will influence chemical reactions which it undertakes. So it's just to put it in proper perspective, even if we think that it's a chain where there is no interaction between atoms which are next to each other, besides that they are, say, distance 1. Even in this case, it's a difficult problem, but in real life, say, if you take an RNA molecule, I mean, it can be meters long, but it's squeezed inside one cell, so obviously it's sort of squeezed in a tight bow, and it's even usually knotted, and that's not a thing which we understand very well, and there is no good mathematical model, even simplified models we cannot solve, but this certainly influences how these molecules react. So for example, in DNA replications, there is some special proteins which help these molecules to unwind and to glue to each other. So it's a thing which is very far from being treated by mathematical physics. But the very simple model and the question which was posed by Paul Fleury was that you take a walk, let's say xn on, well, let's say on some lattice, on, so I would do hexagonal lattice because then this model is integrable. So basically you start from the origin and then you walk in some direction. And this is like 0, x1, and so on, xn. The usual, if you would be just draw all the possible trajectories to be random walk, we very well know how it behaves. We know that if we make n random steps, then if we take all the possible trajectories uniformly, then in n steps will be square root of n away, and it will be a fractal of dimension 2, or just a little bit less than 2 with logarithmic corrections, so to say. But now we condition it to be self-avoiding. So meaning that only simple trajectories are considered. Now it's much more difficult as a model. So the logic is that if you have a molecule, it obviously doesn't self-intersect. And it's much more difficult because it's no longer Markov. So it's if you cut a self-avoiding walk into 2 parts, there are 2 self-avoiding parts. But if you concatenate 2 self-avoiding walks, it might not be self-avoiding walk. And if, for example, this trajectory I can continue 2 possible ways, but if I draw trajectory like that, then it's clear that only finite number of steps are possible afterwards because we cornered ourselves in. So it's really wildly non-Markov. So what Fleury did is the following prediction, that the mean square displacement is equal to n to the power 3/2. Well, it's of the order of the n to the power 3/2. Or you can rewrite it in the way that if we take our trajectory and steps and we box it into a box of size d, then the n will be on average of the order d to the power 4/3. So it's you just, well, so here it's something of the order d squared. So d squared is like n to the power 3/2. So we can show that the walk in a box d by d, on average will have d to the power 4/3 steps. So it will be a fractal trajectory of dimension 4/3. And now there is an interesting story about this prediction, because he made it. It's classical. So it was made in 1948. So it was before the normalization group. So it was Landau's mean field theory and a very neat argument. So essentially, if you have a walk, there are two restrictions. I mean, step number 5 is next to the step number 7. And so step number 6, so n and n plus 1 are always neighbors. And the other restriction is that 2 points, they cannot be x5 and xn cannot be in the same place. So if you treat these things as uncorrelated, you can easily solve the model and you get this number. But obviously they are correlated, because if 2 points are 7 steps away, they are more likely to coincide if you draw the random walks than if they are 100 steps away. It was observed later by another well-known chemist and physicist, Dejean, that the method is wrong, and it's this problem which was posed by mathematicians in 50s, and people tried to solve it. It was forgotten for a while, but then it appeared that actually the method is wrong, but the prediction is correct. So you can actually trace it. In one place he loses something, in another place he gains something, and the number is correct. And he had also a number for dimension 3, which is 5/3. And for dimension 3 is wrong, but only by 2% off or something. And the way how it was sort of found to be correct, though not proved, so there are several approaches. One can try to do here transform metrics. It doesn't quite very well work, but it's more or less in generally same framework. It's just on the borderline, on the endpoint of an interval where the methods work much better. Another way it was done by Bernard Nienhuis, a Dutch physicist, was application of the Coulomb gas formalism. And he first put this on a firm footing. So this was a bit before conformal field theory, and then of course later it fits into the realm of the conformal field theory. So you get all these exponents, conformal field theory with central charge 0. So for example, dimension 4/3 you would also have for a frontier of a percolation cluster, and you would also have it for boundary of a Brownian trajectory. So there are 3 fractals which are the same after the limit. This curve, frontier of a Brownian cluster and boundary of a percolation cluster, but which are different in the lattice. And Nienhuis did it slightly before, and he did several more predictions. So for example, the number of trajectories of length n, it's very easy to see that it grows like some number to power n because of convexity. So if you take so number of trajectories of length 7 times number of trajectories of length 5, since when you concatenate you get a trajectory which might or might not be self-avoiding, it strictly measures the number of trajectories of length 5 plus 7. So it means that there is some exponent, there is some number mu, and so he showed that it's this number mu is square root of 2 plus square root of 2. So it's this sort of asymptotic behavior, and this number would depend on the lattice. And more precisely, it's times n over 11 over 32, and this is a universal term. So this is what we were trying to understand and to prove, so the argument of Nienhuis or CFT arguments, they are not entirely rigorous. Also the Nienhuis argument, which you can't get this Watt-specific constants from conformal field theory, it's also, even on unrigorous level, it requires some leaps of faith, and it's not quite understandable. So what we were able to do is to understand very well this number, and now we're trying to get this other two. And this, this we can also prove, and we have a proof which even Nienhuis understands, but he says that he understands it much better than his own proof, his own argument. First, maybe some remark about what is the Coulomb gas approach. So what he does, he considers a more general class of models. So it's sort of loop representation of n model, or rather of high temperature expansion. So what you do, in our model we only had the curve on the lattice, but now let's allow many loops and possibly one curve, so we fix some boundary condition that there is some source from which a curve starts. So general configuration is sort of more complicated. You can have some loops which take one hexagon or possibly, I don't know, 2 hexagons, or they can be nested, so that there might be big loops which are nested, and then you can add some boundary conditions which will produce a curve. You can do it in a plane, in a full plane, or in a torus, or in some domain if you wish. And then we should write partition function. So what we do, we write the sum of the all configurations, n to the power number of loops, and x to the power length of loops. So essentially what this corresponds to, so there are some very nice special cases. So if we take n equal to 1, then we get the Ising model. And you can do this curve as a high temperature expansion. So those are curves basically running inside spin clusters. But you can also do it just directly, these curves being domain walls. And then if you think that there are plus spins on one side of the loops and minus spins on the other side of the loops, then x to the power length would be just the perimeter of the loop, so the number of plus minus pairs which are next to each other. So x is a temperature parameter, is the exponential of minus reciprocal of the temperature. And n is equal to 1, so we don't cover the number of loops. And these points then would correspond to disorder operators. So we would have here on this side plus, on this side minus, but then there is this point where we create this curve, so there is some monodromy around. Then, well, n equal 2 is just the Heisenberg model. And XY model. And n equals 0, well, we put 0 to the power number of loops, so there are no loops whatsoever. We only have one curve, and we have this self-avoiding walk. And essentially the question of counting self-avoiding walks, it boils down to the question of what is the critical value of x when this model goes through some critical behavior. And well, the first thing which was deduced by Nienhaus was the renormalization picture of this model. So if we fix n, and we take x as a temperature parameter, then rescaling it amounts to change in x, and then there will be 4 fixed points, 0, infinity, and then let's say x tilde, x critical and x critical tilde, and one of these 2 points will be repelling. So there is one critical regime which is attracted to 0, and 0 is a frozen mode because if you count it and you put x almost 0, then you penalize for any loop. So basically you won't have loops, so you will have just very, very few small ones. Then there is this chaotic mode, so there is an attracting point in the middle of chaotic mode, and then there is one critical regime at this point. And the Nienhaus argument said that xc and xc tilde, they are reciprocals of the square root of 2 plus minus square root of 2 minus n. So in particular for n equals 0, you get this point reciprocal of square root of 2 plus square root of 2. And this is what sort of counts the number of self-avoiding walks. Now, what was the Coulomb-Gas approach? So now I didn't look at the clock when I started. So you can cheat.
I guess at 4:35?
35, 45 or 35. 35, okay, very good. And so the Coulomb-Gas approach essentially adds a little bit more into this picture. So we orient all the loops. So we orient loops. And then, each loop had a weight n, so the oriented loop should have weight n 1/2. But we do a little bit smarter than that. We add or subtract iy so that we get some unitary number, let's say mu and mu inverse for a loop. And then the weight per loop can be, so then there are two observations. First, if you have oriented loop, it looks like geographical landscape. So we have a height function, which is measures how many loops with orientation we crossed. So we get height function. Then this new complex partition function projects to the usual one if we forget orientation. Before projection, of course, it's a terrible function because it's not a probability measure anymore. It's a complex measure whose total integral is equal to 1, but total mass is much, much larger. So when you integrate to 1, many things cancel out. Yes?
So this n is equal to 1?
Well, n is equal to 0 for self-avoiding walk, for 1 to Ising, to 2 to Heisenberg.
If it's 2, then y is 0.
Inverse, what's mu inverse?
Yeah, so if n is equal to
Well, it's mu inverse, which is equal to mu bar. So it's a unitary number, so its inverse is just its complex conjugate.
Yeah, but if n is equal to 2, then y is...
Yeah, right. Well, it's basically the thing which happens is that if you want n1/2 to be a real part of some unitary number, then n1/2 can change from 0 to 1. Well, you can also have negative weights, but that's sort of questionable practice. So n is from 0 to 2. And for point 2, of course, there is no imaginary part. So the way it sort of manifests is that at n equal 2, so for these models you have a first order phase transition for appropriate quantities. When you cross n becomes larger than 2, you don't have first order transition anymore, you have exponential decay of correlations, and this is sort of related to these non-abelian models, because if you treat it as a O of n model where spins are on a sphere, so 3-dimensional sphere is non-commutative, and 2-dimensional sphere, well, I mean, the circle is commutative. So actually the boundary lies at between n2 equals 3, and actually it lies at 2 plus epsilon. So this is sort of a neighboring point. And in a sense, what I'm going to say, we understand very well how it should be for Heisenberg model. We cannot prove it, but we understand what is going on. But for other models, there is this complex twist which no one understands very well. So the Coulomb gas I'm going to say, people know very well how to do it in a plane or in a torus, but not with boundary conditions. And really, I mean, no one knows, not mathematicians, neither physicists, so it's a thing which should work, but maybe I will, if you spare me another half an hour, I will touch upon that. So we forget orientation. It's a huge complex measure, or well, real if n is equal to 2, as Leon and Anton pointed out. But do we gain something? Well, besides height function, we gain that this measure becomes local, because we can weight turns of our curves by factor lambda, which is mu to the power 1/6. If it's turned to the left, and lambda, which is mu to the power -1/6 if it's turned to the right, well, lambda -1. And then if we take the product of these weights, the length of the curve, we get either mu if we have a loop counterclockwise, or mu -1 if we have it clockwise. So basically, partition function is the sum over all configurations, product over all sides of lambda to the power ±1 for every side through which we have our curve. So we get partition function, which is a local product. It only depends on the height function, because essentially if we know height function h plus 1, then we know that we turned left. If it's h -1, we should have gone from other direction. So essentially we have height function, and we have probabilities calculated from a local configuration on 3 adjoining hexagons. So when we pass to the limit, it's logical to assume that it will be a Gaussian free field, because that's the simplest thing where there is a random height function continuum and it only depends on the local thing. Indeed, it seems it is, because from that, essentially you can get all these predictions. So the only thing you need to figure out, so it converges, so here there is a height scale, how much you jump. So there is this scale. So when it converges to free field, it converges to free field times some constant. So we need to get this constant, and it will be different for different values of n. And once you figure out, you can do all the predictions. So now we cannot do this. The main perhaps reason is that it doesn't work very well on the plane or on a torus. So I want to have some boundary where it starts working better, but then I don't know how to formulate boundary conditions well enough. Well, maybe I'll say at the end. So what we tried to do, so we tried to find some discrete complex structure on this lattice. And one object which is sort of inspired by these complex weights, which are originally due to Baxter, and also by Kaufman-Fermion for the Ising model, is to consider what happens if we have a picture like that. We have a curve, a disorder operator here, and what happens when we move this point. So what we do is that we look at, well, I mean, for simplicity, we do it in a domain, but one can do it in the full plane, no problem. And we fix 2 points inside domain, or for simplicity, one can be on the boundary. So we look at the pictures like that. So we fix n, z, and so we take the general model, and we look at function f of z, a, well, f of z, but it's actually f of z, a, and omega, and which is basically the same partition function as there. So it's the sum over all configurations like that over the product, and we have n to the power number of loops, x to the power of their length. But then now we have one curve, so the loops already sort of have their lambdas factored together, which gave us factor of n, and we have still to take product of lambda, the length of this curve. But then it makes sense to take another value of lambda for the curve, so we can leave it as a free parameter, then check for which ones one gets something interesting. So we take lambda, so it's another lambda, let's say for this curve gamma. So we get product, the length of this curve gamma, lambda, gamma to the power plus minus 1, depending on whether we do left or right turn. We get a complex valued function on a lattice. So lemma is that for every n, there exists basically unique, well, there are only two, how to say, not there is unique, but there exist two unique. Well, there exists, okay, one unique and another unique x, c, and those are exactly the xc which were predicted by our friend in-house. And for this xc, there exists lambda c, such that f of z is, well, satisfies, it's half holomorphic. Half holomorphic means that it's divergence free. And for n equal 1, it is also curve free, so hence it is discrete holomorphic. So here I speak about some discretization of holomorphicity. So one possible that you ask that the function is a vector field on edges, if as a flow of some liquid through the edges, it has no divergence. So for every vertex, so basically it satisfies two Kirchhoff laws that for every vertex the sum of function on emanating edges is 0, and then also a flow around the face is 0. So.
Determining the sign of the power in lambda?
The sign, so basically you go the length of this curve, and then every time when you turn to the right it's lambda inverse. Every time when you turn to the left it's lambda. So basically it's lambda to the power winding of gamma from A to Z, and now winding is measured not in radians but in pi over 3 radians. So it's winding, if you measure it with radians, you divide by pi over 3. Okay. So actually, which power of lambda it should be, one can guess either from knowing which parafermions there are in this field theory which behave nicely, or from some combinatorial things. So it's actually clear from beforehand what the value of lambda should be, but one can also leave it as a free parameter and arrive where one is supposed to arrive. So what is the corollary of this? So the corollary of this is that, and this is the work with the Go, is that the first corollary is that for n equals 0, x is equal, well, this is sort of, we'll have square root of 2 plus square root of 2. And the way, I mean, I think, yeah, I already once spoke about this 3 years ago here. So, I mean, we simplified the proof since then. The proof actually is very easy. It's like 4 pages. So I would just say what is the basic idea. So we obtain that we have this function, and for x equal to this number, it is divergence-free. Now divergence-free, they satisfy local relations from which you get global relation. The flow of the function through the boundary is equal to 0. So you get that so lemma tells us that for x equal to xc, the integral, contour integral around any contour, for example, the boundary of omega of f dz is equal to 0. Now this contour integral, it splits into 2 parts. First of all, you get contributions of all curves which go to the boundary. And for the curve on the boundary, we know exactly how, when to arrive here, you know exactly how many turns you have to make. It's the same as the boundary does. You can't, if you arrive here making no turns, you can't arrive here making 720 degrees, because if you try to make 720 degrees, you will sort of go overboard in this domain. So we know exactly what will be the complex weight on the boundary. And it turns out that if you choose a nice domain, which is not very curvy, this complex weight will have positive real part. So actually, what one gets from this is that integral of not f, but just the usual sum of n x to the power lengths and to the power number, but we don't have any number, so x to the power lengths for all walks to z, dsz, with some coefficient here, is equal to 0. Well, not quite to 0, because there is also one more point which have to take into account. So the walk can just start here and be of length 0. So there is this point which also gives us contribution 1, because you have to count also walk of length 0. But walk of length 0 is counted with minus sign because it hasn't started yet. So if you calculate this winding, so you get this sort of a relation. So essentially, what you get not the full partition function of a, so we almost get that the partition function, which is the sum of xl over all self-avoiding walks, for criticality is 1. So we don't get it. We get the sum part of a partition function, which sums all the walks inside the domain, gives us exactly 1 for critical value of x. And from this, one can deduce that this is exactly critical value of x, because if these walks give us exactly 1 and we increase x a little bit, we will get more than 1. But then we can stack to this domain another domain, and that it will diverge. So in the plane, the sum will diverge. On the other hand, if we take x a little bit smaller than that, then the sum will be smaller than 1. And then if we do these stacking things, it will converge, because we will have a geometric series. So essentially, from this, we can easily get that zx in the full plane is infinite for x bigger than xc, and is actually smaller than 1 for x smaller than xc. So it means that xc is indeed critical. So this is how it works. Now, if it would have been like for easing, that we would have had a function which is not only divergence-free but also a curve-free. And the fact that it's divergence-free is just some combinatorial consideration which looks at what happens if we take all the walks which go to this edge or to that edge or to that edge, and does some XOR around this vertex and compare. So there is some bijection between the walks going here, here, and here. And if you rewrite this bijection with the correct weights, it gives you the divergence free. If, like for easing, we would also have curve free, then what we would have had is that function f of z is analytic, discrete analytic inside the domain. So you can try to pass to a limit, sending mesh lattice to 0, and get that the function in the limit is analytic, and the only question would be its boundary values. And here it turns out that the boundary values we know, because we know how many turns we make before we arrive at some point. So essentially, so the conjecture is that f is holomorphic, well, at least in the limit. And then if so, we also have on the boundary of omega f, so for this specific value of lambda which we get that f on the boundary of omega is proportional to dz to the power 5/8. So this is a specific value of, I did not say, maybe, well, if someone asks, I can say how one gets this finite number, but together with this finite number one gets the power 5/8. So this finite number is actually cosine of pi/8. Yeah, it's or twice cosine of pi/8. And 5/8 also it comes from something like that. So if we know that f is holomorphic, we get this boundary condition, which is a Riemann-Hilbert boundary value problem, or just Riemann boundary value problem because it's homogeneous. And then we know f, and then from this we can deduce everything, including all these numbers. But that unfortunately we don't know. And then, so that we tried to do, and the other thing which appeared while we were trying to do, and which maybe will sort of invoke some association with one of you, and then I would be glad to hear those, is we tried to perturb the lattice and see whether this thing or some other thing behaves nicely. Now, perturbing the lattice, what we have, we can, well, if we do this lattice, we can split it into triangles in that sort of a fashion. And then we have weights of triangles. So if through triangle a curve goes, then there is a weight x, independent of how it goes. So there are three possible ways. If no curve goes, then the weight is 1. So the question is, can we perturb this and have some weights so that everything would work nicely? So unfortunately the answer is no. It has to do, it's probably the same thing why for transfer matrix easing model you can plug in any lattice, and for other models there is some condition on the weights. So this would have worked only for easing. But what works nicely apparently is if you have a rhombus rather than triangle. So if you have a rhombus, so for rhombus which is composed of two triangles, so there are different possible pictures. So there is, for example, this picture which has weight x. Then there is such a picture which has weight x squared. Then there is this picture which has weight x squared. Then there is this picture which also has the weight x squared. And then, well, of course, there is an empty set picture. So it turns out then we can perturb rhombus to be a rhombus. And then still it is okay, and still there are some integrable weights, but not, well, I can show you from afar a piece of paper where you have those weights, so to scare you off. So it's there kind of, each of them is product of 4 cosines. So there are nice weights which simplify when you have equilateral triangles. And the only commentary is that there is a new configuration which appears, because the rhombus doesn't remember that we have this line. So the new configuration in the rhombus is that you have two connections like that. So it can be maybe better formulated that you have a double H here. So you allow for a double H. And then it turns out that there are some weights which I have not written, but it turns out that there is another function which works very, very nicely, and which we have both hopes for. But so far it's still only divergence free. And another function, so sort of a new function. So it's, let's say f was already used. So g of z is, well, basically you can write that g is the derivative of the partition function g of z, the derivative of partition function where you change the rhombus at z. So for one of the rhombus, we change its angle. So basically, it's like we have this very nice triangular lattice, which is due to the hexagonal lattice. We pick one rhombus, so the original hexagonal lattice is here. So we pick one rhombus in a piece of a covered chalk, and then instead of this rhombus, we insert a rhombus which has different angles. So it's basically looks like angles here are decreased, angles here are increased. So it's sort of inserting a conformal anomaly. So we change angles, total angles at these 4 points, but we change them by minus epsilon these two at pi plus epsilon and these two. So if you don't come into this rhombus, you don't notice it. It's flat. If we would have changed just one angle, then it would have created conical singularity, and the global weight of loops would have changed. So we're just doing it locally, and it turns out that again, sort of same thing. That g of z is divergence free. And G is holomorphic for Ising. Now, since it is holomorphic for Ising, we can calculate it exactly. Now, we don't calculate it exactly in this way, but we rather calculate it exactly, writing it so in Ising these curves are domain walls. So we have to calculate probability of different configurations, which are basically probability of some local energy correlations. It turns out that this nice thing, it's nicely factors in a product of two fermions, and then it's the thing we can do now very well. And the conclusion which happens for Ising, so for example, if we have a domain and we have a picture like that, so it's an Ising with a Dobruzhin boundary condition, so this can be uniformized to half plane by a function phi. So for the Ising, this G is a discrete version, and in continuous it converges to the following function, phi prime over 5. Well, you properly have to normalize, so it's up to a constant what I write, so it's G is, let's say, constant. Well, let's say C is a bad letter because it will be used now. Plus 1 over 24 times the Schwarzen of phi. Actually, with 1 over 24, we had some problems because it first was 1 over 36, then it was 1 over 12, but we knew that it should be 1 over 24, and now it is 1 over 24. Sorry?
24 is nature of
yeah. So here it's just C over 12, and where C, the central charge for Ising, is 1/2. So the question is that well, if we try to do it for self-avoiding walk, it sort of almost works. So for self-avoiding walk, you should have zero central charge, so it should be phi prime over phi squared, and in this case it seems to reasonably well in the continuum setting. It's with a lot of sense factors out in phi prime squared and 1 over phi prime. Well, probably up to minus sign. So basically this is the question. So has anyone seen either in lattice models where you can factor such things nicely, or in zero charge conformal field theory, factoring of the stress energy tensor so that some sense comes out of it?
Any generalization for three-dimensional case?
Oh, well, you mean of self-awaiting walk or what? Of easing model, what do you want?
Maybe for loops or maybe for domain walls or something like this.
No, I mean, one problem, of course, if one tries to do something in three-dimensional case is that in two-dimensional, for example, I mentioned that for the easing model, you can get these curves either as domain walls or by high-low temperature duality as other curves. Of course, if you do duality in dimension 3, then curves are dual to plaquettes, so domain walls are dual to curves. So you don't get self-dual models, so it's more complicated. Now, well, yeah, I know. Smart people always say that it's last time I was giving a talk and Misha Gromov said exactly the same thing. Have you tried looking at plaquettes in dimension 4? And said, yes, I did. It gets complicated. Yes, yeah. In dimension 2, 4 having some model with plaquettes, someone should look at it. Yeah.
Because the boundary motion is in 4-dimensional self-avoiding.
Up to logarithmic corrections, yes, yeah. So for self-avoiding, actually, I should say that like any model has a critical dimension. Now Brownian motion trajectory dimension 2. So if you have two-dimension 2 object, if you cut Brownian motion into halves, and you have two-dimension 2 object, what is the chance that they intersect? If dimension is 5 or bigger, they don't intersect because 2 plus 2 is smaller than 5. 2 plus 2 is equal to 4, so in dimension 4 they have this sort of logarithmic correction, some small logarithmic loops. In dimension 3 they wildly intersect. So in dimension 3, I think that the one thing which one can try first, there was this model which was proposed independently by Greg Lawler and a few physicists, which is called loop erased random walk. You do random walk and you erase all loops. And they thought that it would be the same as self-avoiding walk. It's not, it's different universality class, it's central charge minus 2. But this model, loop erased random walk, it's related to electrical networks, so it's related to harmonic functions, harmonic vector fields in any dimension. It was known to Kirchhoff 150 years ago. So there is a recent paper in probability, which is rather complicated, which says that it has a scaling limit, a random curve in R3 by Gadi Kozma, and he basically does it head-on, 70-something pages, and estimates. And but the thing is that harmonic functions are involved. Maybe one can try to get some exponents there or something. So I would start with this thing. For other models, I don't know. So most of what I say, it doesn't have chance of being applied, but 10% one should try.
Any other questions? Thanks again.